Hey everybody, this lesson number 2, is about converting from hexadecimal to decimal, and from decimal to hexadecimal, and from hexadecimal to binary, and binary to hexadecimal. And essentially, the focus is on hexadecimal as a numbering system, and then how it works with particularly binary to provide some capabilities that make our lives a little bit easier in the computing realm. So, so the objective of this particular lesson is that we would like at the end of it, you should be able to, between this lesson and the homework that you'll get and the feedback from that homework, you should be able to confidently do conversions from binary to hexadecimal, hexadecimal to binary, hexadecimal to decimal, and decimal to hexadecimal with a reasonable accuracy, our usual standard of about 70%. Again, as I said several times in the last lesson, you should be able to do better than that. By the time you've practiced this a few times, it really isn't terribly difficult. It's one of those things you have to be precise and you have to pay attention to what you're doing, and you need to take care as you're doing it, but understanding what you're doing is not particularly difficult to do. It's basic arithmetic. It's just basic arithmetic using a numbering system you haven't used before. So let's press on. We'll press on in a moment to look at some demonstrations as to how we go about on how we do those conversions. But first, I kind of like to touch on the ideas of a why. Why hexadecimal? Why do we do this? And why am I spending so much time on this kind of stuff? Well, first of all, I'm doing this because my experience from the last class was a lot of people had trouble doing the conversions. Even though I would consider this to be very, very basic mathematics, some of the concepts were foreign and we didn't have homework, and so there was an opportunity to practice. So the first opportunity that they were given, outside of, they could have made up their own and tried to work through a few examples, but at the end of the day they didn't. And so their first opportunities are on quizzes and then on the exams, and unfortunately many people didn't do quite so well, and I wasn't really happy about that. So I realized that, okay, we need to have some homework in there, and we need to have some practice, and more importantly, we probably need to see it done. So that's what we're going to do here, is you're going to get a chance to see it get done. So but first, before we get into the nuts and bolts on how that happens, the other thing I wanted to show you was the kind of the why. So let's go ahead and go over there and take a look. So what I have up here is I have the Windows PowerShell program. For those of you who are familiar with older Windows, and we're talking older Windows, well, this is going back to Windows probably before many of you were born, but there was a program, or there was a language called batch programming, and you could do some automation things with it. You do a lot of things with batch programming, and PowerShell's kind of batch on steroids, and it has a lot more capabilities than batch ever dreamed of, and part of it is this particular command here. So what you see above here is you see the command line, all of this up to where it says TJLN with the caret symbol. That's just the prompt. The command itself is format-hex, which is in yellow, and then I included in the quotes the complete locator for the file itself. So we see that in the drive directories and then the actual file itself. And this happened to have been a file I had prepared for last year, when we were in the Python Python programming segment. So And then what we see is the output of that command. Underneath it, we see the path that shows us where it's at. And then in the center, all of this here, this big block right here, is all hexadecimal. Not necessarily obvious when you first look at it that's hexadecimal, but if you look across here, even if you see the fourth set of characters here, the fourth column of characters is 6E. Okay, and that's a hexadecimal number. And if you go further on, there's a 6D and a 6E. They're actually all hexadecimal numbers. So I'll point out that, for instance, 23 here does not mean 23 decimal. In decimal, that's actually equivalent to 35. Why? Well, because this first column, this first digit here on the right, the least significant digit of these two, is 3, and it's in the ones column, so to speak. And so it is, in fact, worth 3. However, the 2 is in this next column, the 16 to the 1th column, or the 16s column. So that's really saying there are 2 16s plus 3 1s. 2 16s are 32 plus 3 is 35. So that's what all of this, so more importantly, it equates to 8. So each of these 2 hexadecimals represent 1 byte. So this is actually a breakout byte by byte by byte, byte by byte by byte by byte. All right. So again, all right, so and if you will, another thing to understand is each of these numbers equates to a code that is used to encode text with using binary numbers. So the binary equivalent of 35 is also the ASCII code for the pound symbol, and that's how you look at it. And then the ASCII code for a space is 20 hex, which is 32 decimal. And so notice that every place, so notice that we have a space, and we have 2 letters, and then another space. So sure enough, what do we got? We've got the pound symbol, which is your 23. Here's your first 20. Here's your 2 letters. Here's your space. So there's a lot of information in here. Where is this useful? How can this be useful? Well, I like to tell people a story about early days, my early days, when I first started, when I first got into the field. And I'd probably been working for a couple, 3 years. We were using a program at the time called Enable, and it was a multifunction program. It had a word processor in it, a spreadsheet, a presentation program like PowerPoint, and some other programs in there. I don't remember. Oh yeah, I think there was a small database, if I remember rightly. So it had a number of different functions in there. One of the capabilities it offered was the ability to apply a password to a file, so that if someone attempted to open the file, they'd be given a password prompt, and if they didn't have the password, they couldn't get into the file. Now, our recommendation to people was don't use that, and it's still largely the recommendation of most security people these days, is don't use a password on the file. If you've got a file that's got confidential information in it, the right thing to do is to, first of all, make sure that it's stored in secure places where only appropriate people can get to it. That's number one. And then the other thing too is, as you're moving it around from place to place, make sure that the method you move it is secure. So if you're going to use it, send it via email, make sure you send it by secure email. And if you're going to transfer it using a file transfer protocol, use the secure file transfer protocol, not just simply FTP. So anyway, regardless, so to continue the story, so the inevitable happens. Some big mucky muck out there decides that he's going to ignore our advice and apply a password to the file. And or some days later, he tries to get into the file and discovers he can't because he doesn't remember the password. So, at this point, the world's coming to an end. It's mass hysteria. Dogs and cats are living together. All that good stuff. This has got to be fixed. So it lands on my desk because I was the senior admin at the time. And so what I did was I opened his file up with a tool very similar to this, to what you see here on the screen, and I took a look at it. And okay, I could see what was going on in there a little bit, but I couldn't necessarily identify how the password was implemented within the file. It had to be within the file. It couldn't be external to the file. It had to be in the file. I knew that. So what I did then was I created my own file, a dummy file. It had almost nothing in it, to tell you the truth. I got a little test message, and that was it. And I opened that file, and I compared it to his file, and again, didn't really provide me any information. But then I got the bright idea, hey, I'll apply a password to my dummy file. And I did that, and I saw what changed. And what changed was the first 6 bytes of that file changed to something. I didn't know what it was. I couldn't read what the password was. But then when I went back and looked at the original copy of my dummy file, all of those were zeros. So I took the editor portion of that program and I changed on my dummy file, the one that I had applied the password, I changed it all to zeros, and lo and behold, I could get it open. So I took a copy of his file, changed everything to zeros, and sure enough, it would open up. So I effectively removed the password, even though I never knew what the password was. I didn't really care to. What I did do was give him access and then a stern lesson about not applying passwords when we say don't apply passwords. Anyway, that's the kind of thing where hex comes into play. As you can see, just by how I mapped between the characters on the extreme right-hand side, and what was going on in there, I can tell an awful lot about what's going on in there. And that's where hex comes into play. And that's why it's useful to know that. So now that you've got the why, let's talk about the how. Let's talk about how it's done. Well, first of all, we're going to do conversion. First of all, let's go and recreate some stuff that you had in the first tables here. One of the things to go to binary, let's think about, first of all, if you have base 16, that means you need to have 16 digits. So what are those 16 digits? Well, 0 through 9 are the same as in decimal. I'm sorry. I don't know why I decided to 9 on the brain. Let's do this. I'm going to go 2, 3, 4, 8, 9, and then the hexadecimal, and then the remaining digits are A is 10, B 11, oops, I'm sorry, sometimes I get thinking ahead of where I'm writing. C is 12, D is 13, and E is 14, and F is 15. Now remember, this is a digit that represents 15. Now, let's look at each of those numbers in binary, and you'll see the pattern. Just like before, there's a pattern. We're going to use 4 bits. And so 2 is going to be 0010, and 1 will be 0011. And notice that as we increment, it kind of increments and changes just as you would expect a decimal number to do. In that, for instance, in a decimal number, say you started with 99 and you added 1 to it, what would happen is you put 1 in the 100s column and you'd set the 10s in the 1s column to 0, right? 100. And this does the same thing. So the pattern is the same. So 4 is I do this every time. Well, let's get back there again. 0, 1, 0, 0, and then 0, 1, 0, 1. See, about this point, I would typically be asking you, okay, what's 6 going to be? 0, 1, 1, 0. Unfortunately, we can't do that. 0, 1, 1, 1, and then 1, 0, 0, 0, then 1, 0, 0, 1, and then 1, 0, 1, 0, then 1, 0, 1, 1, then 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. Okay, that's your binary equivalence of all your hexadecimal numbers. And that's the secret sauce to doing the conversion between hexadecimal and binary. It's just that straightforward. So let's start with a hexadecimal number. Let's just say let's say 3 and F and C and 6. What does that turn out to be? Well, 3 is 0, 0, 1, 1. And F is 4 1s. And C is 1, 1, 0, 0. And 6 is equal to 0, or it's 1, 1, 0. That's it. That is the binary equivalent of 3FC6. It is that straightforward. You just convert each and every digit in the order in which you see them. You can start at the right and go to the left. You can start at the left and go to the right. Doesn't really matter. Just as long as you keep the order the same. And by that, I mean, if you were to calculate the decimal for 3FC6 and the decimal equivalent for 00111111111100011110, they would both work out to be the exact same number. It's that simple. It's just a straightforward either way. So that's starting with that's converting a hexadecimal to binary. And guess what? It's pretty much the exact same process to convert from binary to hexadecimal. So just for grins, let's do I need to put my 0 back, it seems. Alright, oh shoot, I went and put You ever had one of those days? Alright, here we go, folks. Alright, now we converted hexadecimal to binary, so let's do a binary to hexadecimal, and just for fun, we'll do a 0, 1, 0, 0, we'll do a 1, 1, 0, 1, we'll do 1, 0, 0, 1, and a 0, 1, 1, 1. What does this convert to? Again, you just go down. 0, 1, 0, 0 is 4. 1, 1, 0, 1 is, looks like D. How do we know that? Well, that's 8 plus 4 is 12 plus 1 is 13. And sure enough, D is 13. Right? Actually, let me go ahead and put these in here. It's 10, 11, 12, 13, 14, and 15. So 1001 is 9. And 0111 is 7. 4D97. And again, if you were to take this binary number and convert it to decimal, and this hexadecimal number and convert it to decimal, both of them would convert to the exact same numbers. So you see how easy it is to go back and forth between binary and hexadecimal. That's why it makes for such a good, and hexadecimal is similar. It's base 8, and it only uses 3 bits. And so that's the benefit of using hexadecimal. In hexadecimal, you get 4 bits, basically you get half the number of digits coming out of a hexadecimal conversion than you would out of an octal conversion. So it saves space and time, and it's pretty straightforward, and most people can handle the 16 characters. So that's it. I mean, that's it as far as binary, back and forth between binary and hexadecimal. Now, binary to decimal, or hexadecimal to decimal rather, is slightly more complex, and we're talking only slightly, in that, yeah, you may have to do you may have to do a little bit of math, but well, let me be clear about that. You're not doing math. You're going to do a little bit of arithmetic. So hopefully, you know how to do arithmetic. You did it in school. Let's go ahead and see how that works. So first of all, let's start with converting hexadecimal to decimal, and that is a pretty straightforward process. We'll just keep doing 4D97 because I'll be interested in figuring out what that number really is. So let's do a conversion from hexadecimal to decimal. And this is similar to how we did this in the past with binary. We're going to start at each place point, each column, and multiply times whatever the numeral happens to be. And we'll see what our final result is. So in this case, we're in the ones column, and so it's 7 times 1, so this is going to be 7. And then we have 9 times 16, 54, carry the 5. 9 times 1 is 9, plus 5 is 14, 144. So this is 144, and then D is equal to 13 times 256. And so 3 times 6 is 18, carry the 1. 3 times 5 is 15, plus 1 is 16, carry the 1. 3 times 2 is 6, plus 1 is 7. 768 plus 256 is 8. 12, carry the 1. 12 plus 1 is 13, carry the 1. 3328. And then we have 4 times 496. 6 times 4 is 24. Carry the 2. 4 times 9 is 36. Plus 2 is 38. Carry the 3. 4 times 0 is 0, plus 3 is 3, times 4 is 16. That's 16,384. Okay, add them all together. 16,384, 3328, 144, and 7. 4 plus 8 is 12, plus, okay, I'm not sure why I put the 7 down there, but let's do this again. Oh, that's right, I'm sorry. The 7 was one of the numbers we had to add. Alright, now we got it. 4 plus 8 is 12, plus 4 is 16, plus 7 is 23. Put down the 3, carry the 2. 2 plus 8 is 10, plus 2 is 12, plus 4 is 16. Put down the 6, carry the 1. 1 plus 3 is 4, plus 3 is 7, plus 1 is 8. 6 plus 3 is 9. And so our answer should be is 19863 is 4D97. So it's pretty good to be able to express that large number in only 4 digits, right? So we see also the power of hexadecimal, and that it gets to be much larger numbers, even the decimals, really quickly. Now, the last thing we need to do is we need to convert from hexadecimal, from hexadecimal to, from decimal to hexadecimal, because we've done all the others. And just for grins, let's do 4D97. In other words, what we're going to do is we're going to convert 1983. Big number, lots of fun. Let's do this. 19,863 divided by 16. 16 goes into 19 one time. 38. 16 goes into 38 twice. For 30, that makes it 32. 6. And 16 goes into 66 4 times, which is 4. Carry the 2. 4 times 1 is 4, plus 2 is 6, 64. That leaves us 2. Carry down the 3. 16 goes into 23 one time, with a remainder of 7. Right? So our first digit needs to be 7, and we see it is. So now what do? Well, divide 2041 by 16. 16 does not go into 12, but it does go into 124. Let's see. How many times? Looks like maybe 7. 7 times 6 is 42. Put down the 2, carry the 4. 7 times 1 is 7, plus 4 is 11. Which leaves us 12, which means 7 was a good guess. Estimate. More of an estimate than a guess. And we'll carry down the 1. So 16 goes into 121. Well, we know it goes about 7 times again. 7. We already know that answer. With 9 left over. So 77 remainder 9, and sure enough, here's a 9. All right. So next thing, what would it be, class? Divide 77 by 16, and 16 goes into 77. It's going to go in 4 times. 4, carry the 2, 64, which leaves us 13. 4, remainder 13. Guess what? D is 13. So far, so good. And remember, we've got to get this, this number up here has got to be 0. So the whole part of the top bar there has to be 0. So it's the last one. 16 goes into 4. And we know it goes in 0 with a remainder of 4. And there you go. So you see it works that way too. So that's the process. So again, so to sum it up, when you're converting from a decimal number to hexadecimal, you divide by 16 and take the remainder, and you're starting at the least significant digit, moving towards the most significant digit. And when your upper part is finally, when this is finally at 0, you're done. And so, and you just saw it work. So that's the process. It's as hard as it gets. So to think back on what we covered here, remember we talked a little bit about, the value of hexadecimal. Why do we use hexadecimal? We talked about the relationship between hexadecimal and binary. We did a conversion from binary to hexadecimal, and from hexadecimal to binary. We find that in both cases it's very easy, as long as we remember, kind of this middle piece that, I purposely did not pre-print, but I wrote out because the patterns are straightforward and easy to understand. And once you've got this here, the rest of it becomes very, very simple, at least as far as binary to hexadecimal conversion and hexadecimal to binary. Just remember that in each case you're translating essentially digit by digit. So, and so that was the binary to hex, and then from decimal to hexadecimal is a little bit more work. However, it's still not it's not very difficult. So it's straightforward arithmetic. So remember that in converting from hexadecimal to decimal, we just started at the least significant digit, moved our way to the left. At each place, we took whatever the value of the hex digit was, multiplied it by the place value there, and we added all of those numbers together to find out what our total decimal number was. And then in reverse, when we did it in reverse, as far as getting from a decimal number to a hexadecimal number, we just started dividing by 16, and we continued to do that, and then keeping track of the remainders. We actually developed out our hex number as well. And you're done when that dividend, well, it's not really the dividend, whatever your result up there, your the whole part of your result, when that gets to 0, you're done. So that's this process. So remember that the objective here was for at the end of this and doing your homework and everything, you should be comfortable doing these conversions from hex to binary to hex, and decimal to hex, and hex to decimal. You should be very comfortable doing those things. Should be able to achieve that 70% passing grade on your quizzes and exams. The homework will give you some more practice, and I'll try to give you feedback before you actually hit the quiz time. And so, upshot of it is, hopefully you'll do very well, and we'll look forward to seeing you in the next class. Bye.